Okay. All right. So the quiz, it looks like will be Monday for sure. And section 4.3 is what we've been doing. That's the max-min stuff, optimization. And we kind of have those steps to follow. And then section 4.4 is the parametrics. Don't forget about that stuff, right? So we're going to be working on, we're going to do a problem with that tomorrow. You know, remember slope of the path and speed of the particle and horizontal vertical velocity, those kind of things. And then section 4.5 is what we're going to talk about right now, called related rates. Related rates. And related rates kind of has a recipe to follow as well. So there's definitely a possibility of confusion. You read the problem and then, wait, was this the one where I do this or do this or whatever? So it's really important to understand the differences in the problems and why you do one versus the other. So let's talk about that just real quick. A max problem should be easy to identify. I mean, it's going to ask, what's the max profit? What's the minimum cost? How fast can you get there? What's the highest the ball ever got? Those are max-min kinds of questions. These problems, related rate problems, are about, well, just what the name says, rates. So you're going to see, in related rate problems, you're going to see things like this. Inches per year, feet per hour, cents per day, cubic inches per second. You're going to see rate kinds of things. There'll be a time element involved that you don't see in those max-min kind of problems. So there will be a lot of this kind of stuff. There will be a lot of, with respect to time, implicit differentiation. There will be a lot of x primes and y primes and r primes and v primes and those kind of things. In other words, dx dt, dy dt, dr dt, those kind of things, with respect to time. And there will be some implicit differentiation. We will not have to get formulas in terms of just one variable to do our derivatives. Okay? And so from that standpoint, it's actually easier to do. All right, so let's take a look at this first scenario here. And I don't know how much of this you want to write down right now. We'll do an example problem here in a minute. But this says a rectangle is 10 inches by 6 inches whose sides are changing. Think of it like this. Think of it as a situation here where I'm dragging out a rectangle like this, and the sides are changing. Now, as I do that, there's a lot of things that are changing. The length down here is changing. The width here is changing. The area is changing. The perimeter is changing, right? And they're all changing at a certain rate. So many inches per second, or whatever the case may be. So let's write down some of those things just notationally here so we kind of get the hang of this. So for example, in this particular problem, let's call this x and y. What would be the formula for the perimeter of this rectangle? 2x plus 2y. And what would be the area? X times y. But if I wanted to know how fast the perimeter is changing, what would be the rate of change of the perimeter? That would be p prime. Now it would be dp dt, that kind of a p prime, right? It wouldn't be with respect to x. It wouldn't be with respect to y. It would be with respect to t. The t isn't even in the problem as far as a variable. But x, y, and p are all changing with respect to time. So it's like x is really x of t, and y is really y of t, and p is really p of t. In other words, they all have a value based on a certain time. As I drag that rectangle and make it bigger, x and y are all going to have different values depending on what time it is that I'm dragging. Does that make sense? So they're all functions of time. So you tell me what would be, let's see if you're following me here. If this is the p equation, then what would the P prime equation be? Nah, you're following, but that isn't quite right. It would just be 2x prime. Remember how we do implicit differentiation? We do the normal derivative. What's the normal derivative of 2x? 2. And then we tack on an x prime. Plus 2y prime. Yeah, if this was x squared, then the derivative is 2x x prime, right? You do the normal derivative, then you tack on the prime. All right, let's look at area. So area is x times y. What's the change in area? Well, that would be a prime. That would be dA dt. Well, how would you do the derivative of x times y? Product rule. X prime y plus xy prime. Right? Okay, now, this is how we will do so this situation with this rectangle, I drag it, there are a lot of rates going on in that scenario. As I drag that and make that rectangle grow, there's a lot of different rates that are all related to each other. And that's why these problems are called related rates. But notice these will be much different kinds of problems than the optimization we were doing. So there should be no confusion between what's happening, which one of them we're doing. This is not a max or a min situation. This will be a situation of how fast is something happening. So in other words, so now let's go down to part A here. Let's say as we're dragging this, and the rectangle is 10 inches by 6 inches. Let's say that we know the length and width are increasing at a rate of 2 inches per second. Now what did they just tell me there? Which of my labels that I've been using here did they just tell me? X, those are rates though, it's inches, x prime. So what they just told me there is that x prime is 2 and y prime is 2, right? And that's what will happen in these problems. They'll say, okay, you're dragging out this rectangle and the length and the width are increasing at 2 inches per second. How fast is the area changing when the rectangle is 10 inches by 6 inches? That'll be the question. So they'll give you all this information and they'll ask you for one of the rates that is involved in the problem. So in this case, we want to know how fast, let's do perimeter here, or no, let's do the area one here. How fast is the area changing? So we want to find a prime. Well, all we have to do is look right up here. So if they ask me how fast the area is changing, what I would do in the problem is I would find the area first, and then I'd say, now let's do the derivative of that with respect to t. We're not doing the derivative setting it equal to 0. We're not doing a max. This is a whole different situation, right? Derivatives can be used for a lot of things. One thing a derivative can be used for is to find where a function has a max. That's what we've been doing. Look where the derivative is 0, look where the derivative is undefined, look at endpoints, right? Another thing derivatives are about are rates. Rates of change. That's what we're using them for here. So the area of the rectangle is this, the A prime would be this. All we have to do is now plug in our values. So what am I going to put in for x prime? 2. What am I going to put in for y? Yeah, this would be 10 and this would be 6. So we'll put 6 in for y. Plus x, I'll put in 10. And for y prime, 2. And so then we get A prime equals 12 plus 20, that'd be 32. Now, what are my units? Yeah, it's area, so it'd be inches squared per second. Now, if you took physics, I think in physics sometimes they make you, when you plug numbers in, you got to put your labels on them, right? I'm not going to make you, unless you want me to make it. But you got to get the right unit at the end, right? So if you think about this, what was 2? 2 was inches per second, and 6 was inches. So inches per second times inches, that'd be inches squared per second. But usually, if you do everything right, all you have to do is think what you're finding. Oh, I'm finding area. The rate that area is changing. So it's got to be inches squared per second. Okay? And so there you go. So that's how those problems look. Now, that was fairly simplistic, but basically, you'll be given a situation. where things are changing. Now, there might be some things not changing. In this problem, as I drag this out, everything's changing. Area, perimeter, X, Y, everything's changing. Sometimes things won't change. I'll show you some examples. So you write an equation for the thing you're trying to find. You'll do the derivative with respect to t, which means you'll have some implicit differentiation going on, lots of primes. And then in the problem, they'll give you some values that you'll substitute in. You should be able to find the one you're looking for. Okay? That is the type of problem we're dealing with here. So let me show you some examples of what we will do over the next several days. Here's an example of a ladder leaning up against the wall. Now, when the ladder is up against the wall here, okay, at the beginning, now as I pull out the bottom of the ladder, as it slides out from the bottom, X is changing, Y is changing, but the hypotenuse is not. So here's an example where we could label this. One of the problems you'll have when you're doing these is how to label your picture. Now, a lot of people would draw this and label this X, Y, and Z, which would be fine. Now, what equation could I write that relates these? Yeah, Pythagorean theorem. So a lot of people might label this X, Y, and Z. Now, I would suggest not labeling this Z because it's not changing. I think you should put variables in for the things that are changing. They vary. They're variables. The things that are not varying throughout the movement, the motion in the problem, go ahead and plug them in right away. But let's say you forget to. So let's say you do this. All right, so what is x squared? Now let's do the derivative. What's the derivative of x squared? 2x, x prime, because we're doing the derivative with respect to t here, right? We got rates with respect to time. Plus 2y, y prime equals 2z, z prime. So now you go through and you say, I'm going to plug my numbers in. Now it says we have a 6-meter ladder against the wall. Its bottom is pulled or pushed at a constant 1/2 meter per second. So let's say we're pulling it out. So what is the 1/2? 1/2 meter per second. Wouldn't that be x prime? So that'd be the rate that x prime is changing. So that would go right there. Okay? We got 2 right there. All right. How fast is the top of the ladder sliding? So how fast is, so what are they looking for? They're looking for y prime. When it is 5, let's just do 5 meters up the wall. So when y is 5. Okay, so that means I'm going to put a 5 in for y. I'm trying to find y prime. So I don't know what that is. What is x then? Yeah, I could find it from my original equation. I've got y is 5, I've got z is 6. So at that instant in time, it'd be 36 minus 25, it'd be 11, the square root of 11. 3 point something. Yeah, let's just call it 3.1, that's whatever. We would use more decimal places, but you get the idea. I'm just kind of quickly going through this. And then what would be over here? Well, you'd say 2, and then what's z? Z is 6, and what's z prime? 0, very good. Because z is not changing. So the derivative of it is 0. And so that wipes out the whole thing anyway. So the whole side is just 0. So I think in the beginning we should have just put a 36 there to begin with, 6 squared. And then when we did the derivative of 36 would just be 0. Either way it should work, but the idea is you've got things that are changing. If some things are not changing in the problem, anyway, we've got all our numbers. We can find y prime, and away we go. I know I went through that pretty fast, but I'm only going to assign you a couple to try to see if you get the hang of it. Then we'll talk a lot more about it tomorrow. Okay, here'd be another one. We got a boat being reeled in. Okay, so here's the rope. So the length of that is changing. The distance the boat is from the dock is changing. But this wouldn't be changing, right? But again, we'd have another Pythagorean theorem kind of problem. So that would be the equation we would set up. Here's another typical problem we have. We have a tank being filled with water. Okay? Well, the volume is changing. The height is changing. The radius is changing, right? Matter of fact, everything in this problem is changing. as you go along. So we might want to find one of those things. Here it says, how fast is the water level rising? So that would be H prime. So we'd be interested in H prime. Okay? Here's another one. This is one of my favorite ones. Okay? I didn't make this, by the way. I'm not that smart. But got a guy walking. The shadow is changing length. It is growing. You ever seen that? Obviously, when you walk along, you see your shadow is growing. So it's growing. How fast he's walking would be the rate of change of the green section here. The tip is actually moving at a certain rate as well. I think it would actually be the combination of how fast he's walking plus how fast his shadow is growing. So again, you'd have some right triangle kinds of stuff going on in there. All right. So these are the kinds of, these are some of the types of problems you can run into where you've got multiple things moving in connection with each other. How do we find the rate? If this one's moving this fast, then how does it affect this? And how fast does that move? I think for the most part, they're easier than the optimization problems because they're easier to set up, okay? But we sometimes run into troubles in kind of what to plug in and when to plug it in and those kind of things. If we look on this, they kind of give a recipe. I wouldn't write this down right now, but we'll just talk through it. Related rate problems always can be recognized by the words increasing, decreasing, growing, shrinking, changing. When you see those kind of words, you're thinking of rates. Follow these guidelines. Make a sketch. Almost always an important thing. Label all the sides in terms of variables, even if you were given actual values of those variables. Okay, now like we were saying, if something's not changing, you could go ahead and plug that in. Now they write that down here a little later, and I'll show you that. Now they say make a table of variables. I would not make a table of variables, but you saw me write down some of those variables. I wrote down x prime, I wrote down y prime. What am I trying to find? What are they giving me? That kind of thing. Some are constant, some are changing. Find an equation that ties your variables together. If it's an area problem like we did, you write an area equation. If it's a right triangle, which a lot of problems we do are, then set up Pythagorean theorem. Or maybe a trig equation, like a right triangle trig, like a SOHCAHTOA maybe. Sometimes that, because maybe the angle, right? There was the one I didn't show you was a searchlight problem. Maybe you got this searchlight, right? At what rate is the angle changing? That kind of thing. So you might have a right triangle trig kind of a thing. Now, once you set it up, you can plug any of your variables that are constant, like the ladder wasn't changing. So you can put in the constants. Never plug in a variable that's changing at this point in time. Then step 5 is differentiate with respect to t. That's when your implicit differentiation comes in. And then after you do that, then you can plug in the other stuff, all the rates and stuff that they give you. Plug those values in. And then you should be able to find the missing piece. Okay? That is kind of what you saw me go through, and that is what your job is for related rate problems. So our homework, I'm going to change it a little bit here compared to what we were doing or what I said before. So we still got a little bit of time left if you want to work on these or finish up whatever it is you were doing earlier. In section 4.5, I think it's on page 253, we're going to do number 4 and number 7. That's it. So that's different than what the your assignment sheet says. So that, I think that's right, Paige. Let me look here. Yeah, I think that's it. So in section 4.5, so we got a couple of problems with related rates, kind of like the one we just walked through a little bit there. And I know I didn't give you a great a lot of time to think that through, but okay. So try those two, and then finish all of the circled problems in the business packet. All right, all of the circled problems in the business packet. So that's where most of your time will be spent. And remember, on the website, I think I showed you this, under today's assignment, under the assignments section, under Tuesday, I've got the business packet answers. I've got a PDF of those answers there. that you can use to help you out there.